All right, number 19 on section 3.5 says find each limit if possible. All right, now if you look at this and you think about the Bobo Botten eats DC, that's, you know, if you think about that theorem that kind of summarized that for us, that's the short way of remembering it. If you look at this, which power is greater, the numerator or the denominator? Well, it's the denominator. So that would be bigger on bottom. So that's Bobo. That means that the limit is going to be 0. The limit as x approaches infinity is 0. Let's try the math on this and see what it comes out to be. We were used to thinking about that Bobo Botten eats DC as a way to find our horizontal asymptotes. Let's see, though, if that also holds true for our limit. Let's just go through the math and see what happens here. If we wanted to actually go through and show that this would be true, we would say, okay, let's take, we're doing the limit as x approaches infinity. I'm not going to write that on every line just because it's messy to write, plus it takes up so much room. But what I could do is divide out the biggest power, which would be x squared. So I'd have the top, and I would divide each term by x squared, because x squared is the biggest term. And then on the bottom of my fraction, I would take each term and divide it by x squared. Because if I plugged in infinity, you know, into my x terms at the onset before I started doing what I'm doing right now, I would have gotten infinity over infinity, which is called the indeterminate form. So this is one way we can take care of it if we actually want to see that this works. I'm dividing everything top and bottom by the same thing, so it keeps all the expressions the same. All right. 5 over x squared, that would be 5 over x squared, if I simplify this, minus 2 over this x to the 1/2. If you subtract the 2 on the bottom is bigger than the 3/2 if you're looking at this fraction right here. So you'd end up with x to the 1/2 on the bottom. And then on the bottom, the denominator, you'd end up with 3 minus 4 over x squared. Now, if we plug in infinity, what I'm going to do to show that I'm plugging in infinity is I'll just put a red infinity everywhere there's an x. 5 over infinity would go to 0. 2 over infinity would go to 0. And then on the bottom, I'd have 3 minus 4 over infinity would go to 0, so it would be 0 over 3, which is 0. So we can see that the Bobo Botten eats DC also helps us find our limits of rational functions as well as our horizontal asymptotes. Let's go ahead and do the B and C parts here just so you can see, you know, just different technique, how we can use this technique. The B part, they have the limit as x approaches infinity. And again, that's hard to read, but you know that's what I just said, so you're going to have to listen and also look at the screen. That's x squared plus 2 over x squared minus 1. So if I were going to come in here and divide everything out, what I would do, x squared is the largest term, so it would be x squared plus 2. I'm going to rewrite the function first, and then I'll come in and divide the largest exponent is a 2, so I'm going to divide each thing by x squared. All right. In this case, before I simplify all this mess, I kind of know what my answer should be, because the exponents are the same on the top and the bottom. That's exponents are the same. Divide the coefficients of those terms. My limit should be, if I use the Bobo Botten eats DC, 1 over 1 is 1 is what it should be. But let's verify that that's what's going to happen here. Now, x squared over x squared turns into 1. And this x squared over x squared turns into 1. And so now, what that leaves me with, I'll just go ahead and continue in blue here, is 1 plus 2 over x squared over 1 minus 1 over x squared. Now, I'll plug my infinity in for my x, and I'm just going to do that by putting the infinity over the x's here. Okay, so when I evaluate it at infinity, I get 1 plus 2 over infinity squared goes to 0. And on the bottom, 1 minus, okay, 1 over infinity squared also goes to 0. So I have 1 over 1, which is 1. Again, the Nabobo-Botten EATS-DC works for both our horizontal asymptotes, and it also works for our limit because our horizontal asymptotes are where that limit is approaching. It doesn't get there, but it approaches that value. Okay, we'll go ahead and do part C of 19. Limit x approaches infinity of 5 minus 2 x to the 3 halves over 3x minus 4. Okay, you need to be able to show the algebra on this and go through that as well as plug it in. The problem what happens is if you always use the little memory device, that's really just the theorem is all it is. And it's okay to do that and know what your answer is going to be, but if you don't practice doing this, when there are other harder things that you've got to do, you won't have had the algebra practice, and you'll find those things harder. So I want you to show me the algebra on these problems as well as using the memory device, because anybody can use the memory device. You can, but you need to be getting your algebra skills. That's what makes calculus hard is the algebra, so we're going to make sure we're working on our algebra skills as well. If I look at this one and I just think about the theorem and think about Nabobo-Botten EATS-DC in order to help me, know what the answer is going to be, this is going to be bigger on top. Well, Nabobo-Botten, bigger on top. Botten means there is no horizontal asymptote. So we're pretty sure the limit is not going to exist. Limit does not exist here, is what we're pretty sure the answer is supposed to be. But let's go through the math and show that that's true. There's one thing in order to be able to just look at it and use that little memory device and say, oh yeah, that's what it's going to be. It's another thing to actually be able to use the algebra and show someone that it's true. So I want you to do that. If you can't do that, expect if you take further calculus courses to have trouble, okay? Because you have got to practice this stuff. It's going to, fall in. You're going to have trouble with further calculus if you can't get through the algebra on this when you get to college. All right, so if I let the limit approaches infinity, and I want to actually do this algebraically, the biggest power I see here is to the 3 halves power. That's like 1.5, isn't it? And it's bigger than the x to the first power on the bottom. So what I'm going to do is divide out by the largest power. I'm going to divide out x to the 3 halves. I'm going to do it to every term, just re-representing each term. Okay, so what I end up with before I plug in the infinity is 5 over x to the 3 halves minus 2 over 3, and we'll have x to the 1 half on the bottom, because 3 halves minus the 1 on top, which is, I can write as 2 over 2, would be 1 half that would go on the bottom, and then minus 4 over x to the 3 halves power. Now, if I come in and everywhere I have an x, I plug in infinity, and I'll just do that with red here and write over the x, just since I want to save some room on the iPad. If I plug in that infinity, I have 5 over infinity minus 2 over 3 over infinity minus 4 over infinity. So if you look at what happens here, this is after I've plugged it in. I'll draw an arrow to show you where I'm at. This becomes 0, this becomes 0, and this becomes 0. So I have negative 2 on top, and I have 0 on bottom, but the limit does not exist because this is in itself another indeterminate form, or you can look at it as if we made it like 0.00000000001, that's going to approach infinity. So what we can observe is that the limit does not exist, just as the Nabobo-Botten EATS-DC told us would happen. If you remember, you used Bobobot and EatsDC back in pre-calculus, but you didn't know why it worked. Somebody just told you it worked, you know. You really have to know about taking limits in order to understand why it works. And that's why, you know, we're going through the trouble of doing the algebra here so that you buy into the fact that, yes, this really does work. This is an algebraic way of figuring that theorem out.